Hey, it's 7 o'clock. Welcome back, folks. Any questions you folks would like to discuss before we get started today? Maybe a couple announcements would be a good start. So far what we've done is we've defined the length of a curve. We've not proven, but possibly derived a little bit portions of theorems of how to come up with the length of a curve. Then we rotated that curve and saw how that can extend to surface areas, provided those surfaces are specifically surfaces generated by some kind of revolution, about the x-axis or about the y-axis. Then today, we're going to break into section 8.3, look at centers of mass of certain regions as well, and that will conclude our explorations of applications in chapter 8. There's a lot more things we could talk about. Probability theory, we could talk about things along the lines of hydrostatic force, but we're only going to cover centers of mass in 8.3, just so that we're not bogged down too long on the various topics. That's also the best supported topic in the actual textbook in that section. Then we'll be moving on to chapter 9. We may not get to chapter 9.1 complete on Thursday, so it's kind of a possibility on the homework assignment. If we do get there, the whole assignment will bounce, so it's not too long. But we'll see where we end up. Any questions so far then, before we start? Okay, I'd like to do a couple more problems from 8.2, just look at a couple stranger type of cases so that we're fully prepared for the homework. The homework assignment is just the 3 problems, mainly because if you do these 5 problems in the prior section, you'll feel like you're really doing the same kind of things. The interpretation changes between length to surface area, but it's very, very similar type of work. So for the sake of not being too redundant, it's a little bit shorter in 8.2. Let's give these new types of strange problems a try. So the questions once again say to let the curve C be given by, the first one we'll look at is x equals 1/3 of y squared plus 2 to the power of 3/2 as y varies from 1 to 2. So 1 is less than or equal to y is less than or equal to 2. So now we have a curve. If we'd like, we could calculate its length, but we're going to rotate it. So let's say for this curve, we'll rotate the curve about the, let's go for, on this one, x-axis. Then, upon doing that, we now have a surface that we can look at. It's not a solid, it doesn't have any interior, but the surface that we generate, we could possibly calculate the exact surface area. On this one, we should be able to do that. So the instructions say to calculate the exact surface area of the resulting surface. Then to get to this kind of problem, we do have formulas that are going to help us out. In the 8.2 notes, there's 2 versions of formulas that we're looking at, dependent upon which axis we're going to rotate about. And when you look at these formulas and you organize them in the note cards, it's important to know that this is almost identical to the formulas for the arc length. The new feature is the 2 pi due to the rotation, and in this version we have an f of x, which is a type of radius about that rotation, or we could have something else, like say this one with a g of y in our case. So to determine what really goes there, it could be g of y or just the variable y, it could be f of x or just the variable x. A sketch is really helpful. So that's probably where I'd start on every homework problem. Take a look at a sketch. You don't have to include it in your assignment. That's great for scratch work. So the sketch of this particular curve looks about like this. I would only care about the relevant domain as y goes from 1 to 2. So we have a variable y as the independent variable x as the dependent variable, and from 1 to 2, the height starts off at about 1.7, and then we increase to about 4.9. Not exact coordinates, but enough for us to get a picture of what the curve looks like. So about like that is our resulting curve. Then we're rotating this about the x-axis. So the rotation goes this way. So that's the setup of our problem. And if this was, say, an actual exam 2 problem, you would see just about everything here, except for possibly that. I don't know how to include that on a Microsoft Word document. But everything there will support us on getting through the problem. Any questions first before we get started?
I just have a question.
Yeah.
So if it's rotating about the x-axis, and we've been usually having y as the f, or I guess the g of y. So is that always the case? And it's rotating the x-axis, will it be y and vice
Not
versa?
necessarily.
No?
And that's what makes this problem weird. We're rotating about the x-axis, however, the independent variable is variable y. So this is like this different case where normally,
Oh, I see.
if we had a variable y here and we rotate about the x-axis, that would have been the very first formula that we covered, this one right here.
Okay, that makes sense.
But now we're changing the roles of the variables x and y at the same time, rotating about a random axis. And that's where the sketch comes in to help us out. Because it's not entirely clear, unless we have a very good mental picture of all 4 cases, what the formula should be. But with the sketch and knowing the direction of rotation, and having a really rough idea of what the surface would look like, either kind of sketch a shadow copy of the curve as it's reflected, but keep in mind it's also rotated through the board, we can imagine that the resulting surface looks about like this maybe. So this is not quite a bowl, there's a hole there through the bottom of the top, but some strange surface we've generated. As y varies from 1 to 2, we're going to get the surface area S equal to the definite integral from 1 to 2. There will be a 2 pi there, and what goes next is really the key to the entire formula. So we can visualize a variable y being anywhere between 1 and 2. If I place my variable y here, this is just for me to get an idea of the rotation. We would go up to this point, from here to here, and the rotation would go about like that. I'm only going to just draw a line segment, so not the full 3-dimensional sketch of that point rotating. I need to know this radius. What would you say that radius would be there with the bracket? Would it be a variable x or variable y? You heard whispers of y, possibly? How many for y? Yeah, I agree. By this diagram here, if you imagine this line segment being dragged down to that position, its length should be y. So in this picture, we would have a 2 pi y so far. We're still building the formula. If we rotate about, say, the y-axis, let's just briefly say what that would have been. I'm going to erase this very soon. If we rotate this way, I would have had this as my solid line. In which case, from here to here would be a height x, where x is all of this stuff, which would be input into our integrand. But if we rotate this way, then we get just a variable y, because y is an independent variable, that's all we'll use there. We don't have to solve this for y at all. Does that make sense so far? Okay, so from the diagram so far, next thing we can throw in here is either a ds if you prefer, or, well, we'll need to know what ds is. So another way to go about this is to write, the answer is the definite integral from 1 to 2 of 2 pi y times the square root of 1 plus, this will be in Leibniz notation, dx dt squared. And because y goes from 1 to 2, there must be a, I'm not sure why I put a y there, oh, dy down below and dy on the outside. So that's our full formula. Then we just have to walk through the motions of calculate the first derivative of x, square it, and then so on down the line, which we might have done about 8 times so far. Any questions so far with that setup? Okay, so it should feel very similar to what we've done before. However, we did change the rules of x and y, and rotation about the x-axis implies just a variable y there and nothing more. But from here on out, it's all the same kind of algebra. Let's start with first derivative. So if that is our x, let me just copy it so I know what I'm dealing with. If x is a third, multiplying y squared plus 2 to the power of 3 halves, then you can either go x prime if you prefer, or dx dy would be equal to 1/3 by the constant rule. Now by the chain rule, we first do derivative of the power function to the power of 3 halves. 3 halves comes down, and the new power will be 1/2, or a square root. Then we throw in the inner function y squared plus 2, multiplied by its derivative, which would be 2y plus 0. So just a 2y. And that would be our full derivative dx dy, provided no mistakes were made. How's that look to everyone so far? Okay, next thing we need to do is square it, but maybe let's simplify it a bit first. We don't want a huge mess on the chalkboard. So this 2 and this 2 can cancel, the 3's will cancel. So we have next that dx dy is equal to y times y squared plus 2 to the power of a half. Then let's square that whole thing and see where we end up. So dx dy squared implies all of this stuff squared, which will turn into a y squared times y squared plus 2 due to the power canceling the square root. So this is what we're looking at so far. So we have our dx dy squared. We have to eventually simplify this as much as possible and hopefully be able to take a square root. So we might as well multiply this through to see what we end up with. So now we have y power 4 plus 2y squared. And we've tackled this portion of the entire problem so far. We're ready for the plus 1 portion. Does that look all right so far? Okay, so let's add 1 to this essentially. We now have that 1 plus dx dy squared is equal to y power 4 plus 2y squared plus 1. We mentioned before that these integrals are typically a little bit easier because throwing in a variable, or an entire function in fact, outside of the root, gives you flexibility. Things like u substitution suddenly become better options than arc length. However, we still should try to endeavor to simplify as much as possible. So if we can take the root, that would be the best option. So if we look at this, if we're about to take the square root, our hope is maybe it factors. It doesn't have to factor, but quite a lot of them are rigged so that in fact would happen. So if we split this to y power 2, we have to use positive signs. This can split as a 1, and then we can hope. Does it look all right as a factorization? Yeah, that actually works. That means the algebra is going to reduce massively because we will be able to take a square root on this. So this is turning into y to the power 4 plus 1. So if we go to the very next step, just take this square root, that would be square rooting this huge set of equations. Oh, forgot my power 2 there. It would become y to the power 4 plus 1. Well, it really should be an absolute value, but a common theme in calculus courses are that absolute values double the amount of work you have to do in a definite integral. So the domain is typically rigged so that the variable gives you a positive value. Well, in any case, y power 4 plus 1 is always positive, so we can't cancel that power with the square root. So all of that stuff, y power 4 plus 1, will go here, and we have to multiply it by y. Question first?
Shouldn't it be y squared plus 1 squared, or?
Oh, it should be. That was a weird copy mistake. Thanks for fixing that. Should be y squared plus 1. I think I put my power 2 here. Forgot it there. So that should be y power 2 plus 1. Thanks for spotting that. Other questions or comments so far? Okay, in this particular problem, what I really want to avoid is carrying an entire definite integral with all of its random notation through every step of the algebra. So let's extend to multiply it by y. That's just one tiny little extra step. So if we multiply this by y root 1 plus dx dy squared would become y cubed plus y. I guess that's not a huge step to say there, but keep in mind that could have been an entire function. We may have had done a substantial amount of algebra there, so it could have been a good time saver. So y cubed plus y goes all the way here. We can factor out 2 pi and integrate from 1 to 2, y cubed plus y dy. So really all of the fighting is really in the algebra, getting the powers right, allowing the factorization to work, so that we have antiderivatives we can throw in there. So the problem is essentially done at this point. We just have to go through the final motions. Any questions at all so far? Okay, so let's get our two antiderivatives. We'll have 2 pi, we'll multiply y to the power of 4 divide by 4, plus y to the power of 2, divided by 2. Then evaluate from 1 to 2, which could be a good amount of work. Next, this is 2 pi, and I'll go with a bracket this time. 2 going in here will be 16 divided by 4, so we should get a 4. 2 here will be 4 divided by 2, so plus 2, minus, now we have a fourth plus a half. And that's the evaluation. Last thing we could do is simplify it, get a value. But if you were to have stopped at right this point on a Calculus 2 exam, in some sense, good job, because you're doing great test taking strategies and moving on and doing the major calculus portions. So that would be full credit on exam. I'll take that as full credit on, say, a homework assignment as well. But let's go through and work it out to just see what we get. So we have 2 pi, 2, a fourth plus a half, we could call this, say, 2/4 would be 3/4. So 2 minus 3/4 multiplies 2 pi, so we could call this 8/4. Really very tedious. And if you made a mistake doing all this, you can't lose credit because it's not a calculus mistake. This will be 2 pi 8/4, which was minus 3/4, so times 5/4. Will give us all together after cancellation 5 pi divided by 2. So that would be the exact surface area. You could say units squared, but we never put a particular unit of that surface. Any questions with that so far?
What would be 5 pi over 4?
I did cancel with a 2 there into that 4.
Oh, okay, I see what you did.
But let me see if I got the same answer. I got 10.5 pi. I have 2.5 pi. I'm not happy with that. There could be something wrong there. Anyone see a mistake with the arithmetic? So evaluation from 1 to 2. 16 divided by 4 is 2, 4 divided by 2 is 2, then we got a fourth, plus a half. Looks like 3/4. So we are looking at 2.
Did you associate 2 pi before you did your 6 minus your fractions? Did you do like 8 pi plus 4 pi minus a 4 pi plus?
I did all that last. I worked just inside out. I got 2 minus 3/4, so I called 2 8/4, which gives us 5/4, multiplied by 2 pi. You know, I could have made a mistake before. How do you folks feel about that? Might come back to it. I felt pretty good about that work. 5 pi divided by 2, I'm off by a factor of a little bit. But that's okay. Possibly there's a mistake there. Any questions or comments about that so far? Yeah.
Did you add the 4 and the 2?
Yeah.
The 4, oh, these right here?
Yeah.
That would have been 6, wouldn't it? Aha, so if that's a 6 and we get a common denominator of 4, that would become a 24 minus 3 would have been times 21 divided by 4. So the cancellation would be 21 halves, which is 10.5 pi. We found it, thank you. So that was the issue, adding 4 and 2. So if you mess up adding 4 and 2, you can't lose credit. That's a tragic way to get off the right value of 10.5 pi. Any questions about that so far? So arithmetic is our enemy, especially when it's a night class. That is the first thing to go, I think, arithmetic. But the process is really maneuvering through the algebra and the setup itself. If we get those 2 things down, then that would be considered full credit. Any questions at all so far about that one? Okay, so there are strange problems because we are changing the roles of x and y, which is uncomfortable already. We're rotating by a non-standard direction about the vertical axis, which is what we should call it, when the derivation was rotation about the horizontal axis. I'll leave it up to you folks. Should we try one more like this, where we do a horizontal axis rotation with the interchange variables? Does that sound helpful? Okay, let's do one more, and we'll call these 2 sections completed. So let's change the situation by the curve C is going to be given by something else, and we're going to rotate this curve about the other axis, y-axis. So really same instructions, but a new curve, which will be x equals negative 1/3 times y to the power of 3 halves plus the square root of y, and we're changing the domain for the variable y to go from 1 to 3. Okay, so we're taking that strange curve. This function is now a decreasing function. Rotate it about the horizontal axis, y-axis in this case. This will be bringing us back to really the first problem that we did, except that the roles of x and y are different now. So let's get a rough sketch of the surface, or the curve itself rather, and then we can imagine or try to sketch the surface. This one looks about like this. So we go from 1 up to 3. At 3, we intercept the x-axis, and at 1, we're at height of exactly 2/3. So our curve looks about like this. So if we were to rotate this thing about the y-axis, this is the y-axis and this is the x-axis, due to the form of the function, x being solved for makes this a function in the variable y, then we would get a shape that looks about like this. So we have some kind of bowl type thing, so not a ring type of thing. It's strange because, keep in mind, this is a surface, so there's no solid there. You could 3D print it, but you're forcing a thickness to it, where there is none here. But once again, if we just want to have an idea of the surface area, this time y is going from 1 to 3, so we'll do the definite integral from 1 to 3 of 2 pi. Then we have to decide if we're just throwing in a variable x or if we're throwing in a variable y. To do that, we just need to visualize the direction of the rotation about the y-axis. Implies, if I pick a valid y has to range specifically from 1 to 3. These are always random picks, so I'll just decide it's right there. Then we would be going up to this height, and this line segment would rotate. Well, really, the line segments aren't part of the graph, but this point itself would rotate down to there. And what is really critical is this radius of that rotation. So what would be the variable for that radius? Would it be an x or a y in this case? Yeah, this time we're going up to a height of x. Given a y, we have some value x, which depends upon y. So that means we have to go 2 pi x, and the difference this time is all of this is truly our x, whereas in the last problem, because we rotated about the vertical axis, we just got a variable y, which we distributed in. Okay, so we have 2 pi x, then it's a ds like before, or if you prefer, we can jump right to 1 plus dx dt squared, or I'm really wanting a t there, dx dy squared times dy. And that's the form of our definite integral. So now we're ready to calculate. Any questions to that step so far? Okay, so last one, we're going to go through all that algebra of first derivative of fx with respect to y. So let's wipe this out. So we have here negative 1/3 times y to the power of 3 halves plus the root of y. Let's go with a x prime this time, since that's valid notation. It's okay to change it up if you like. X prime is just dx dy. So first we get negative 1/3. We take the derivative of y power 3 halves, producing coefficient 3 halves, and reduce this by 2/2, so that it's now a root y. Plus, then by the sum rule for derivatives, derivative of root y will give us a half. The new power of root y is y to the power of negative a half, so we just produce a square root to the denominator. And that's our first derivative so far. We really don't have much to cancel on this one, but we can cancel the 3's to get negative 1/2 root y plus 1/2 root y. Now we're ready to go on to the next step. Any questions so far to that stage? Okay, so then by the form of our definite integral, step 2 would be to square the whole thing. So we'll go to x prime squared, which is this squared. Let me just copy it out so that I know precisely what's multiplying what at every turn. So we take that times itself, which looks pretty horrible, but there's cancellations all over the place, particularly with the exponents. So if we multiply here to here, that would be positive 1/4 root y times root y gives us 1/4 y. So that's our first bit. Then way out here to here, first we'll get to negative 1/4. Second, root y in the numerator will cancel the root y in the denominator. So we're getting our standard negative 1/4, which indicates there's a particular way this problem is rigged. We might expect to factor this one. Multiply here to here and we get the same thing, only because we're squaring this. Last bit is here to here. When we multiply that way, we get plus 1/4, the root y's in the denominators, multiplied to give us just y itself, to the power 1. So that's the result of x prime squared. Hello, all right so far? Okay, next step, just add 1 to it. So we can say that 1 plus x prime squared is now equal to, say, y divided by 4. All of this is really negative 1/2 if we combined it. We're adding a constant of 1, so 1 minus 1/2 would be plus 1/2. Then plus 1 over 4y, which is interesting because this problem feels massively different from the ones we've seen before, but this is possibly deja vu for a lot of people, right? We're dealing with the fourth, which adds to negative 1/2. If we add the constant 1, everything is now perfectly rigged for an immediate factorization of 1 plus x prime squared equals, we can go root y divided by 2. Really, we're going backwards from what we had over here. Then plus 1 over 2 root y. If you double check on how you FOIL this one compared to how you would have FOILed this one, we're really getting the same kind of result, except the middle term is 1/2, and then the outer is positive y divided by 4. Does that make sense so far? Okay, so that last step of getting the factorization is critical because without it, we may have trouble with that square root where the only way we can really go any farther is a Simpson's rule or a trapezoid rule approximation. If that does happen in your homework, if you did your best, you just didn't have time for office hours to ask questions about it and you know you're stuck, you could just carry on with, say, a trapezoid rule, and I would give substantial credit to that, even on an exam, since it's easy to make the tiniest mistake somewhere, and now the algebra is just not going to play along. You can still get some points. But our next bit is take the square root of everything. Oh, I forgot my power 2 once again. So power 2 on that because we factored it. Whoops. Does that make sense so far? Okay, now let me take the square root of it. 1 plus x prime squared, square rooted, would be the square root of all this. So we get root y divided by 2 plus 1 over 2 root y. Once again, no absolute values because that quantity has no potential to ever be negative. So we have that value now. The next thing we have to do is multiply it with x. So let's just take one more step down here. I'll pull out the 2 pi, integrate from 1 to 3, but now x is this, so we have to throw that in. Negative 1/3 y to the power 3/2 plus root y is our x. Now we move over to the root. That's where we worked so hard, finally factored, got it down right. We have to multiply that by root y divided by 2 plus 1 over 2 root y. Then finally dy. So that's where we end up next. And it's a bit of a nasty business because nothing really rescues us that we've gone through some chapter 7 on. There's no integration by parts that's going to work for us, for example. What we have to do is go back to first principles, just multiply it all out, FOIL this result, then do term by term power rule on it. And that would do the job. Questions before we start? Okay, so we have to take all of this, multiply it. Let's just keep carrying on since we've already started it. This is now equal to 2 pi, definite integral from 1 to 3. Now we start multiplying again. Here to here, the power of y is really 1/2. Let me put in the powers just to assist us in the multiplications. So So we multiply here to here, the power on y is now going to be 4/2, which reduces to y squared. So we get negative 1/6 y squared going first term to first term. So there's some cancellations there, at least with the powers a little bit. Here to here, we get negative 1/3 times 1/2, so it is a negative 1/6. Y to the 3/2 times y to the 1/2, we're really visualizing it like this, but that's a subtraction rule. Overall, this would be y to the power of 2/2, so just y. Does that make sense with that product so far? Okay, then we just redo it, distribute root y through. So here to here, this is root y times root y. That means it's really a y over 2. And this is kind of lucky in the sense that I think it is worth the extra step to just combine those like terms, rather than having more antiderivatives, more evaluations to account for, and possibly make little mistakes on down the line. So I would combine that in the next step. Last bit is root y times 1/2 of root y, so the root y's would cancel, that being the numerator, that being the denominator. So we just get 1/2 dy. And we're just about there. That's finally a definite integral that we can go and get antiderivative with immediately. One final step, we could say that this is 3y. Let's multiply by 3y divided by 6. So we can combine those terms. There it is. We get all together the 2 pi times the definite integral from 1 to 3, negative y squared divided by 6. This will become 2y squared divided by 6, so altogether 1/3. Not y squared, but just y. Then finally, plus 1/2 dy. So once we evaluate that, we are getting 2 pi. I usually just leave it on the outside, bracket this out, and work on, let's go with parenthesis, work on the evaluation of that antiderivative. So we get negative y cubed, which means 3 must multiply 6. So negative y cubed 18ths. This is a really nasty looking one. Here we get y squared divided by 6. And here we have y divided by 2. We want the definite integral of all of that from 1 to 3. So it's tedious, but at least it's all there. And if this were, say, an exam problem, you still have one more step to do. As long as you do the evaluation, I would consider that sufficient amount of work for full credit. So let's evaluate it. To get 2 pi, I think this time I'd want a bracket. We're throwing in 3, so that's 3 cubed negative 27/18 plus 9/6 plus 3/2. Now evaluation at 1 will give us minus the entire group of an 18th plus a 6th plus 1/2. And my claim is, you may want to double check that, but if you carefully evaluate all that, you should get 16 pi divided by 9. Let's take that as a shortcut this time. Is that all right with folks? Okay. Once again, for emphasis, if you did stop right at this stage on the exam, I would consider that full credit, since that is very tedious to spend that amount of time in the exam setting, working those things out. But that's essentially how these go. You should feel like there's really just 2 versions of the formula, 8.2, where you're only throwing in a variable x if it is a horizontal axis rotation. You're throwing in a variable y if it was a vertical axis rotation, and possibly we've interchanged the roles of x and y. I'll make sure the axes are labeled and the plot is produced on an exam setting, so they'll have a good orientation of what goes where. Any questions so far with these kinds of problems? Okay, these are probably, quite possibly, the hardest definite integrals we'll see all class, because any small misstep in working out the square root portion causes horrible side effects in trying to get through the integral. So there's not a tremendous amount of them in the homework. But for the next section, 8.3, it's a bit of a break compared to what we've done. We're going to start looking at centers of mass. And what we want to do is build up in the one-dimensional case, the two-dimensional case, to finally the two-dimensional continuous case, where we'll look at a solid region R. This region, sometimes called a lambda, is visualized as having a definite thickness, maybe a thickness of 1 inch throughout the entire region, and it'll have a fixed density as well. So a uniform density, call it rho if you like, Greek letter rho. So what we'd like to do is, if it has a uniform density, uniform thickness, decide where you would put a pinpoint in this position so you can bounce it from below. So imagine a table with one leg, which is very, very stable. So that's what we're trying to achieve. To do that, we can build on ideas from the one-dimensional case, the two-dimensional case with point masses, until we're ready to do two more kinds of integrals. One for the x-coordinate, the center of mass, one for the y-coordinate. Any questions before we start then? Section 8.3. Okay, there are more things in 8.3 we can look at, but we are going to skip hydrostatic force, mainly because the book does not support those homework problems too well with their short two examples and all the varieties they ask in the problems. We're also not going to do the theorem of Papyrus. It's a cool theorem, but there is just not enough time. Oh, it's not even on the notes. So the final example can safely be skipped as well. But let's move over to 8.3. 8.3 is called Centers of Mass. Let's name it that because that's what we're doing. And centroids. Okay, so this is our setup. We're going to take ideas from the one-dimensional case, where we would visualize something that looks about like this. We have a point mass here in some random location, which I'll call M1. So I'm imagining that all the mass in the system, where I connect a rod to another point, is either here at M1 or here with mass N2. So we have some kind of rod with uniform density, uniform radius, but we're going to assume that that mass along this rod is negligible, and all of the meaningful mass is at M1 and N2. So our job is then to decide, if this were some teeter-totter and these are children, where should we put the fulcrum so that their legs are dangling forever and they'll never get off? So depends on the masses, right? So if this is a very large child and this is a small child, it could possibly be here. I will call this the fulcrum. So we're looking for places where the whole system will be stable and balanced forever. So what's now relevant in this system is, how far did you have to go from